Okay, so welcome back to the last lecture of the course. Again, thank you for being here. So the idea for today is the following. I won't get to do everything I planned, but I'm not that far. First of all, I think that it's quite an interesting topic for the last year, the tensionless strings. I started talking about it last time. I'm going to more or less summarize what I did and say a few more things, which I think are kind of nice to give a geometric interpretation of what's happening. Again, when I say geometric, tensional strings means really a very stringy geometry. The AdS space is very small, so geometry is to be taken with a grain of salt. Then I'm gonna make a few comments about what happens in the holographic picture beyond k equals 3, which was a bosonic point at which there were many features related to the tensionless AdS3 cross S3 cross T4 model. That will be the first half, and then the second half is talk about kind of a different application of the formalism to what is known as little string theory, and then we get to where we get. But let's start with it. Okay, so last time we started doing the tensionless point. So the idea was the following. So in 2018, Eberhard, Gaudiel, and Gopakumar proposed that first string at AdS3 plus T4 at n5 equals 1 was exactly dual to the symmetric pair of story called T4 with n1 copies. So this is 1 n1 F1 strings, and this is the number of the files. The symmetric pair of story called so this is a supersymmetric setting, and I was trying to argue last time that many of the important features interesting features are there in the bosonic model on AdS3 plus cross the internal manifold, where this must have for the total central charge, which is the AdS3 one, which is dk plus k minus 2 plus the central charge of the CFT associated to the internal manifold, has to be 26. And then with the ghost is the usual critical theory in the bosonic version. And so I argue that most of these features survive at most of the interesting features in this limit survive at k equals 3, and for long string operators at 0 radial momentum. Which means that the J, which is usually 1/2 plus IS, S is the radial momentum, so this is not here. It's just focusing on k equals 3 and J equals 1/2. In this setting, then there are those nice things that happen. We saw that the spectrum is exactly, well, the H, remember, is the weight, the holomorphic weight in space-time theory. And we saw that by solving the Virasoro condition, we got something like this. Got something like, exactly, make a mistake. 3/4 omega squared minus 1 over omega plus 18 over omega, which is exactly the spectrum of a symmetrical refold with n1 copies, since the maximum value for omega is n1, of some theory, some seed theory, where this seed is exactly 6 times k, which in this case is 18. This case is 18. Not only did we see this for the correlators, but we also try to argue that not only did we see this for the spectrum, but we also try to argue that correlators localize on configurations where the holomorphic covering maps which go from the worldsheet to the boundary of AdS3. So in our notation from Z to X exists. I'm not going to go through the whole discussion of the correlators. We went into pretty much into a lot of detail on how to compute correlators of a spectrally fluid operator. The idea is that if you want to compute some correlator like this, well, normally I would write this with H, J, H, omega, X, and Z. Those are all the, well, Z is the insertion point, and the rest are kind of quantum numbers of the model. But X I can interpret as a coordinate on the boundary. Since I'm going to restrict here to all operators with J equals 1/2, then I can just remove this from here. And we tried to argue over the last couple of lectures that it was very useful to find a function, which was a holomorphic function, which near each of the zi's behaves as the corresponding xi plus some numerical some coefficient minus times z minus zi to the omega I plus higher corrections in z minus zi. But the main point is that this has to be holomorphic, and it has to be such that it gives you the function at least from the insertion point in the worldsheet to the insertion point on the boundary, and has to have the next few orders in the Taylor expansion have to be vanishing up to the order indicated by the spectral flow index. Okay? If you find some function which does this, then actually coming and computing the correlators is quite easy. Otherwise, it's quite complicated. And when you do it, but this function is not guaranteed to exist. If I give you a set of xi's, zi's, and omega i's, which are all the data you need, there's no h here. So if I give you a set of xi's, zi's, and omega i's, then it's not true that such a function can always exist. It is true for 3-point functions with such that the sum of all the omegas is odd. Then it always exists at the genus 0. But in general, it's not true. And so the question is, so asking that the correlators localize in configurations where the covering map actually exists is a non-trivial condition, but it is actually the correct solution in the tertiary string case. And you can show that. Well, I did explicitly. I used explicitly these maps to show you what the 3-point functions look like. What happens is that at the tensionless point, you can actually use such maps to solve these recursion relations in H or in the y variable that I was using the last couple of lectures, these differential equations. You can actually solve them exactly for any n, also for any n-point function, and that gives you a non-trivial solution for all of the correlators at the tensionless point. And the non-trivial solution looks like this. It's a non-trivial solution to all of the recursion relations. Remember that there is one recursion relation for each vertex operator in the correlator. Then the solution looks like this. So this thing here actually becomes it's a sum over all possible covering maps of the product of this, what is usually called covering map data. So these numbers, this numbers here, if I fix this to 0, 1, infinity, for example, in simple functions, but more generally they can depend on the x's and on the z. So there's just the simple dependence, the h dependence is all contained in this factor. And then you get some normalization, which I was also ignoring last time, which depends on the omega i's if you want. And then from this, which is kind of the most interesting piece, so from 4 to 10 of delta functions doing this, and then some function of all of the which depends on the actual covering map they chose. So when you read this formula is the following: you have a set of say n vertex operators, which again depend on the x's, the z's, the h's, and the omegas. You find the covering map. So these delta functions here tell you that that the result is 0 if if a map that satisfies this property for all of the vertex operators doesn't exist. This is the localization part of the formula. I'm missing the default one. So if you don't find this function, if this function doesn't exist, then the correlator is 0. But if the function exists, then the dependence on h, for example, which is what these recursion relations are all about, the dependence on h is actually fixed in this simple way. So you compute this function, you tell me what these quantities are, you put them here, and the dependence on h is just that. And then there is some non-trivial, some normalization factors, the localization thing, and then something that only depends on the insertion point. But the main point is that this actually simplifies your life a lot when you're trying to do a holographic comparison, because not only do you solve these correlators as a function of x, z, and the omegas and the h's, it's also true that if you want to compare with the holographic correlators, so say you didn't know that the symmetric orbit fold was the dual theory here. If you want to actually show it, you want to compare all the different correlators in the theory. And in order to compare, what you have to do is you have to first integrate over all the I. So you have to integrate over the insertion points of the boundary operators. This is the usual thing, right? In implicit string theory, you integrate the insertion points of the operators all over the worldsheet. So you need to do this computation. And in general, if you're not at the tensionless point, actually, even for unflowed correlators or whatever, for 4-point functions, this is actually a very complicated thing to do, this integral. Carry out the integral. For example, just for 4-point functions in the unflowed theory, this was analyzed in the original Maldatena-Woody paper, and it's actually a long computation. You have to be careful with the different singularities that you have in the set plane and so on. It's a bit of a mess. But once you do, you should be able to, that the thing you get should be the holographic CFT correlator, provided you have normalized the operators correctly. But here it's very simple to do because of this delta function, right? So these go from 4 to n because the first three I fixed 0, 1, and infinity. And this immediately tells you what you have to do to integrate over the Zi. To integrate over the Zi, you have some Jacobian factor, and then the integral is just trivial. Okay? You do this integral, you compare with the, for example, the symmetric orbital correlator, and you find that the dependence here in particular, for example, dependence on the weights, is exactly what you would expect. This is kind of the final result of what we were discussing last time. And so what I want to do now, before going away from the tensionless point, is to try to give a geometric interpretation of what's happening. Any questions on that?
Sorry, but your deltas looks like to be evaluated delta of 0 because gamma zeta j is equal to xj, and the correcting terms are zj minus zj.
Yeah,
at the end of the day, it's delta of 0.
What this is telling you is that so imagine I give you this function for a general z and a general x, right? And a general set of x's and z's. In general, there is no map specifying all these things. These delta functions are just telling you get a non-zero result only when the z and the x's align such that that map actually exists. And when it does, you get the divergence, but because you're integrating over z,
okay,
in order to compare with the boundary theory, then that goes away.
Okay, I understand what you mean.
Okay, so can we give a geometric interpretation? So first of all, why would it be possible? I want to do this in terms of the what's closer to geometry in this model, which are the Wakimoto fields. So you should remember we have this field called gamma, beta, and d phi in the holomorphic sector. And in principle, saying that these fields are actually holomorphic is just an approximation. In principle, when you're inside AdS, there is an interaction term, and you cannot ignore it. And since you cannot ignore it, then there are corrections to these fields being holomorphic and so on, and you cannot just use the pre-field description. However, because we are looking at long strings at j equals 1/2, these are long strings which stay on top of the boundary of AdS. I don't know, for example, in the Lorentzian picture, we had some strings that were like this. We had some very easy solutions, which were just cylinder-like, which go around, the worldsheet goes around the boundary circle omega times. And this solution had something like, so the classical solution in the Euclidean language was just z to the omega, for example. And the phi was related to, so it's phi 0 plus the log of like this. Log of mod z. So this is the classical solution describing this configuration. That would be just for the path integral for 2-point function. This is the Lorentzian picture, and here I'm writing it in the Euclidean. But if you remember the first couple of lectures, this was easy to read off. And because the strings stay very much near the boundary, the interaction term, which was something like this, Okay. It was something like this. In my notation, square root of 2 over k minus 2 pi. This was the interaction term, and it goes to 0 at pi going to infinity, which is exactly the boundary here. In the boundary in this coordinate is at pi going to infinity. This was the only interaction term in the Wakimoto action. So if I just ignore this term because I am at very large pi, then the free field description works. And in this region, we have gamma being holomorphic, beta being holomorphic, and d phi being holomorphic, and these are free fields. Okay. So in this language,
yeah. One question. So phi going to infinity, what do we mean by that? Like this is the action of a 2D CFT, right?
Yeah.
So that's the.
What I'm saying is that I'll be considering like small fluctuations around some worldsheet which is very far. This phi is going to be very large, and then there are small fluctuations on top of that.
But phi is a field, right? Because we have d phi. It's a field that we're.
Yeah. So in the Wakimoto description, phi is a field which came from the geometric description or the metric of H3 plus. So the Euclidean version of AdS was something like this.
Okay, but then if it's a field in my CFT, if I'm saying that phi goes to infinity, is that like saying, okay, then that isn't that like saying that phi has a VEV and that VEV is large?
Yes.
But then I'm breaking conformal symmetry of my worldsheet if phi has a VEV.
If I look at the classical configurations that are associated with the vertex operators that I'm looking at, then the effect, the vacuum expectation value in that solution would be large. Yes, not that I'm not using that from the start. I'm saying that this would be a. I'm only considering operators for which, for this reason, this approximation would be accurate. That's all. Okay. Any other question? Okay. Then I can use I can think about using the Wakimoto description, and this will give me an accurate idea of what's happening. If you remember, in this setting we had three currents, which were J plus, J3, and J minus, something like theta gamma squared, then some. What is it? This. What is here? But anyway, it was something like this. Was some number here, d5, and then some other number here, 5, which k. Okay, so this was the free-field realization of the three currents, and something I didn't say, but which is useful now, is that the actual realization of spectral flows, of a spectral flow transformation in these variables, is like this. I take gamma to z omega gamma, beta to z minus omega beta, and d phi minus omega root 2 1 over z. So this is what spectral flow does at the level of the Wakimoto field. And then from this I can come and compute what is the OPE what are the OPs between spectrally flowed operators? One second. Okay, right here. You can come back and compute what are the OPs between the sum of the Wakimoto fields and the actual operators I'm considering in this correlator. So operators again with J equals 1/2, any H satisfying the physical state conditions, any omega X and Z. And you can show that what you get is something like this. This is X, I, T, plus like this, plus higher order. That's for one, and the other one is something like this. That okay. So for now, let me focus. These are the two results, but let me focus on the first formula, the one for gamma. If you look closely at this formula, first of all, you can ask how is it possible that some X is appearing on this side, right? That's a bit odd. The reason for this is that if you remember, we can kind of translate the whole expression in X from from some xi to the origin, right? So I kind of move everything in X and I put the X here. And you can check that if you do the usual operations I was doing, so you take something like this on your gamma and something like this, which is what you would call gamma at some point X and Z. What you get is just gamma of Z minus X. And the reason for this is that the J0 plus in this language, if I just erase it, the J0 plus is the zero mode of beta, and beta is the guy that has a non-trivial OP with gamma, right? So beta is the guy that has a non-trivial OP with gamma, which was something like this. Then out of all the, I expand this in a series. I take a series expansion of this. I only act once, and then it's done, and that once gives me this X here because I have an X here. So moving gamma from a point X equals 0 to a point X means just doing this translation here, which is reasonable because gamma is basically the geometric field, the field that gives me closer to parameterizing the boundary, and then moving in X is just moving in gamma as well. And that's why if I translate everything to X equals 0 here, I move the X to the side and I get gamma minus X. Okay, that's fine. And the second term, so this is why I get this X here. And the second term is interesting because I get Z minus I to the omega I. And the reason I get Z minus I to the omega I is because I shifted gamma like this when I do spectral flow. Okay, so normally on a field with with no spectral flow, gamma would shift m to m minus 1. Here it does the same, but it does the same when I act with the shifted mode, which comes from this choice here. So, okay, fine. So now what happens if I try to use this inside some correlation form? I'm doing everything wrong because I don't want to erase this formula which is in the middle of the graph. Okay, so now the question is, what does this look like? I take some correlator. And I try to think about what this does. When I try to think about what this does, I just, for example, near some point that I, right? I just use the OB of gamma with the corresponding field, right? Take some J. So I use the OB of gamma with this field, which is exactly what I wrote there. So this gives me something like xj times the full correlator plus z minus zj to the omega j times the same correlator, but where I shifted as hj to hj minus 1, right? Because I shifted the index here. I changed the weight by acting with gamma. Okay, so I do this, and I get something like this. But now the really nice point, and plus higher order correction. Now the really nice point is that I have the solution for the correlator, right? The solution in a attentionless point is exactly given by this formula here. So I know what happens when I shift h to h minus 1. I shift h to h minus 1. The only thing I do is I change this exponent here, right? So I just add some little ai. That's what I do. So I can just rewrite this as x plus aj z minus zj to the omega j plus higher order correction acting on the original correlator, right? Because I just have this factor here, and the only thing I did by shifting h was to add some power of a.
A doesn't depend on gamma.
On gamma? What do you mean by gamma? Gamma is the field.
The covering map. Because I thought in this sum, I thought you just fixed the
A is a function of the covering map I'm choosing.
gamma. Yeah. But now you're taking it out of the sum.
Because for a given configuration, there's a sum, of course. I have a sum here.
Okay.
I was thinking about situation where you have only one, which yeah, you're right. Okay. So, but this is nice because this is exactly what we expect the covering map to do, right? It's exactly the expansion of the covering map that I have here. Okay, and you can continue checking this for the higher order, and it always agrees if you use this formula. So the main method is that you can always find something like this. And the conclusion then
Because if there is no gamma, then you mean that this thing is zero. It's regular.
yes, exactly. So there's no expectation, there's no value of gamma inside correlator. So inside correlator, And this tells you that that's exactly what you would expect. You have a classical solution which tells you that this gamma tells you how this, for example, in the cylinder solution that I was writing, how this gamma takes the worldsheet coordinates and maps to something that's like a cylinder in this case, like that parameterizes what would happen at the boundary. You have correlators which localize exactly at points where the covering maps exist. And then what you see is that inside any correlation function, you can always replace gamma, the little gamma, the Wakimoto field, with the actual covering map that you use to compute the correlation function. And in this sense, it's very nice because you can really start to see the worldsheet itself as the covering space of the boundaries. But of course, that's a correlator dependent statement, right? For each correlator that I choose, for each set of omegas, x's, and i's, I may or may not have some map, some covering map. And then if I do, the correlator is non-zero, and in that case, the expectation value of this gamma inside that correlator is exactly the holomorphic covering map. Is it more or less clear how you get to this? Yeah?
When there are several gammas in the sum, it means that there are several worldsheets that interpolate between your...
Exactly. Yeah, there are several contributions. And this is exactly the way you would compute in a symmetrical response. You take your insertion points, you try to trivialize the boundary conditions by going to some covering space, and you have different contributions depending on the different ways you have to do it. Okay.
Then there are these theorems, right? Certain number of insertions, this capital gamma is completely fixed.
Yeah, so for example, for
Riemann-Hewitt's theorem or something.
yeah, exactly. You can do, well, actually, there's a nice. So I get into that. But okay, let me just comment on that. There's actually a very nice story which is written on the notes, which I wrote a couple of months ago in the notes, and then today there was a paper by Andrea Day and friends, actually doing a very similar computation for this. The fact that this is true inside correlators is actually quite subtle. It's actually quite subtle because it's true that with the OPEs you can show that the behavior of gamma near each of the vertex operators is exactly what you would expect for the covering map. But it's subtle because this covering map has that property there that near each of the insertion points. But there are also some number of once you fix the map, there are also some number of simple poles of this map. This will have some residue, will behave like this. For example, for 3-point functions, when the covering map exists, A goes from 1 to n, and a genus 0. A goes from 1 to n, where n is 1 plus half the sum of omega I minus 1. So this side, right? You should think about this formula as something like this. Write it more clearly. You think about this formula as something like this. Okay? And this is fine when you go near each of these points, but here there are poles, there are a set of poles, right? This is not a choice. You cannot choose it. Once you give me the set of omegas, x's, and z's where this function satisfying these conditions there exists, then you actually find the function. You can compute it, for example, in the case of 3-point functions as some ratio of finite hypergeometrics. You compute it, you give, and because it's a ratio of hypergeometrics, it satisfies what you want near the insertion points, but it's gonna have folds somewhere. You just find it exactly. For the case of 3-point functions, otherwise sometimes it's a bit more complicated and so on. 4-point functions you can find, etc. At least at G0, 0. But the point is that here there are poles, right? There are a set of poles, set of big N poles, which, from the point of view of this correlator here, should not be there, right? Because there's nothing inserted at those points, right? There's no operator here where I'm inserting at one of these points here, and then there's a non-trivial OPE between gamma and this operator, which gives me some pole. There's nothing. So that identification is actually quite subtle. And the answer to that is to remember how you write this, how you compute these things in using perturbation theory, right? If you have your perturbation theory, you should have something like this, then a set of poles, a set of vertex operators, and then you should insert here what are called screening operators, or the, let's say, the interaction term, some number of times. Let's say, I don't know, R. Okay. Say you have some free field here, you have your action, which is the Wakimoto action, so the free action plus the interaction term, or this interaction term is what we wrote before, something like this. So these are just the kinetic terms for gamma, beta, and phi, and this one was the interaction term up to some number here, which was something like this. And here I already said k equals to 3, sorry. Okay? And so, actually, if you're doing perturbation theory, you have to compute the corrector by bringing down a number of these interaction terms, right? But then what happens is that the phi field, we have these fields gamma, beta, and phi. And what happens is that the different vertex operators are charged under the current, which is d phi. And the number of vertex operators, the number of interaction terms that you should include in order to get the non-zero correlator is something that cancels the charge. So you bring down a number of them. And you can compute what's the charge of each of these operators. It's exactly written in the OPE of the d phi. Let me write it here. D phi at Z with bi was something like -1/2. And you can see that the charges of each of these operators are exactly given by 1/2 omega I minus 1, which is exactly the thing that appears here. So the number, for this to be non-zero in perturbation theory, the number of times you have to bring down an interaction term is exactly given by the charge of these operators here, plus the background charge. And the background charge, if you remember, we had that the background charge for this q phi was -1 over square root of k minus 2, which in this case is just -1 for k equals 3. And so you see that the number of interaction terms that you have to bring down is exactly the number which is here, the sum over the omegas of 1/2 minus 1/2 omega I minus 1, plus this -1 here from the background charge, and it gives you exactly that this is non-zero only if the number of interaction terms is n. Exactly this big N that was here. And then from the localization on the locus or the covering map to this, you can argue that once you have these integrals, but the only places that contribute to the actual correlator is when these guys, when you hit the point where the insertion point is exactly given by these values here. And since you have a non-trivial OPE between gamma and beta, this gives you the pole that you need to actually finish arguing that this holds. This is true. And this, in these numbers here, is what you were asking to answer. That this, the counting of, for example, this is the Riemann-Poisson formula for the case of genus 0 and so on. So the identification here is very nice, and it's actually much more, contains more information than it looks. Okay. Any questions so far?
Is there a meaning to the values poles are looking? The Z, A star. You say they are completely fixed. What do you mean?
Yeah, they are. Once you ask for the covering map, they're fixed.
What's happening there? That's one point. The insertion point, I guess. No? That's the insertion point of this additional terms.
Yeah, it's the only place that contributes in this.
Yeah. If you put these terms anywhere else, they don't contribute, and then at these points they.
I think the meaning is just that. It's just that you need to put them there for the correlator to be non-zero, and you need to put them at those points for the map to exist.
For string theory amplitude, I think you have to integrate over the worldsheet. So that, right? So
I'm integrating.
yeah. So the S matrix will not depend on, or okay, like that.
Yeah, of course. Let's say there are special points in the worldsheet.
Yes, I'm integrating. What I'm saying is that in this integral over those insertion points, the only contribution will come from delta in z minus zeta.
So they are like diagonal points. Higher trust points on the worldsheet.
Okay, and the geometric interpretation doesn't end there, because you can play the same game now with D5. You can use now this OP and do the same, and you can ask what this thing corresponds to in terms of the covering map. And you can show. I try to do the other one in a bit of with some detail. I won't do it for this one. You can show that this gives you exactly something that behaves like minus 1/2 the second derivative of the covering map divided by the derivative of the covering map. Right. You can show that this always holds. So the identification is a bit more complicated, but you can show that this function here has exactly the properties that near each of the insertion points it behaves exactly like this. Okay, so this seems kind of not so easy to interpret, but then you know that if you take this identification seriously, so this being minus 1/2 the derivative of the log of gamma, and then this is that, then you can show that for the actual field phi inside correlator, you can identify that this should be phi 0 plus minus in this case the log of the absolute value of the derivative of the covering map. Okay? So this is the same type of identification as here, but it's a bit more complicated. And you can ask why this makes sense. And the reason is I think, particularly nice, especially for, again, those who were used to, those who at some point did some computation in a symmetric orbifold or something like that, using the Matur papers. But it's nice for two reasons. First of all, if you look at the cylindrical solution that I wrote on the other blackboard, or something like this, I told you that I had gamma being z of omega, right? This goes omega times around the boundary. So in this case, for this correlation function, this is exactly the covering map. For a 2-point function, this is exactly the covering map that I would expect. It's just z to the omega, right? You go to the covering space, it just covers my physical space omega times, because the worldsheet goes omega times around the boundary. So this is exactly what I would expect. On the other hand, for phi, I showed that I wrote before that I got something like this. But if you take this covering map and you put it here, you just easily check that this formula is exactly this formula here. So again, for a classical solution, this is satisfied. Not only that, but the point in the symmetric orbifold correlator when you compute them in like Lunin and Matur in 2000, the idea is that you take your physical space X and you go to some covering space Z, which I can write as gamma minus 1 of X, such that you trivialize the boundary conditions, right? You have a series of, operator, for example, of twist operators, omega 1, omega 2 at x1, omega 2 at x2, etc. You want to compute these correlators, where what these operators do is they take different copies of the theory. So you take some field x1 being in the copy n1, some field x2 being in the copy n2, x3 being in the copy n3. And if you say, for example, I want to act with sigma 1, 2, 3, what this does is it tells you that when you go once around the physical space, the boundary conditions are twisted so that x1 goes into x2, x2 goes into x3, and x3 goes into x1. That's what the twist operator does. These twist operators have some weight, they have some further properties, and you can compute this correlator, and this is kind of the main thing that you want to do in symmetric orbifolds, and then you just stress it to do what happens with the rest of the operators. But the main point is you have a lot of copies of your theory, and you want to allow for these non-trivial boundary conditions and compute what they do in a correlator. And the way Lunin and Matur do it is they show that if you go to a covering space, which is defined by the different insertions that you have here, you trivialize those boundary conditions, and then it's just some trivial computation. But then the point is that you have to take care of the conform when you go from X to Z space. You have a contribution from the conformal anomaly. For example, if you go from a space dx squared in more usual formulas, and you do a coordinate transformation, which brings you from this, which was dx bar, that space originally, and you change to e to the 2 phi, say e to the 2 phi dz bar. Then, for example, at the level of the partition function, you can show that the partition function computed on space with metric with a line element ds, so the space of x, let's say, is exactly corrected by the partition function in the z space by some factor SL, where this SL is some Liouville type action for some field phi, which is defined exactly what transformation you did. Okay? Okay, fine. So this is how I'm not going to details, for example, I'm not going to details obviously, but you always get some. So this is the idea is that you end up, if you're talking mostly about Swiss operators, here you end up with something that's very easy to compute, but this is the more complicated contribution, and this comes from some type of Liouville action for this field phi, which parameterizes the coordinate transformation you did to go to the covering space. But now you know that we know exactly what transformation we're doing. We're doing a transformation such that gamma of z is x, right? So the dx bar is exactly some factor like this, is z bar. So if I identify this here with this e to the 2 pi, I find that the Liouville field in the Liouville-Matur computation is exactly up to a constant, something like this. Right? And this is, in my opinion, a very nice result because, well, first of all, it reproduces exactly the formula that we just got from the worldsheet inside correlators, but it tells you exactly what this extra Liouville field is. So there are kind of two operations going on. You take your boundary theory and you go do the actual computation of the correlator in some covering space, right? What covering space you go to is defined by what twisted boundary conditions you were putting here. And in doing so, you get some simple thing plus an extra contribution. This extra contribution can be computed in terms of some scalar field phi. And what we just did is telling you is that this extra scalar field, which was not in the original theory, is exactly the radial field, the radial direction in AdS. Because phi is the guy that parameterizes going into the AdS space. So again, in correlators, you identify this extra field that's just an auxiliary field in the symmetric orbit for computation with exactly the field, the extra direction given by holography. And again, I don't know exactly how much of this is generalizable to arbitrary things to other settings of holography. I hope I work on this because I hope that a big part of it is kind of teaching us some interesting lessons about how holography works in general. And you can have and there are different ingredients here which are very nice. The worldsheet of the string, of the dual string theory, is exactly the covering space of the boundary theory here. This auxiliary field that appears is exactly the radial direction inside AdS, the extra direction. And to me, at least, intuitively, that's quite nice. So that's as far as I go with the tension string.
Great. So to understand this better about the radial direction, so is if I'm in the tensionless limit, my AdS3
is string size.
Yes. Is string size.
Yeah.
Okay. And if it's string size, also that means that I don't have really locality in AdS.
In AdS, yes.
Yeah. So then I don't. Why does it make sense to define
For the
radial direction?
In some sense, you do.
The worldsheet, yeah, is local, okay, but I'm really talking about AdS, right? And so in AdS3, there's no radial direction because there's no locality at all, right? I mean, it's just something we write, but
I agree. It's
like if you compute some actual local observable, it won't depend in a local way on phi.
It's that's why I said at the beginning. I said geometric interpretations between quotes, right? There is some AdS3 space, but it's very hard to give it a geometric interpretation because it's string size.
Can you, I don't know, can you probe?
Yes.
How
So
local it is
for example,
in this phi?
For example, there's a very interesting recent paper, I think from last year, by Bob Knighton, and I can't remember if Gardil was in there, etc. Where they show that although as I was arguing for these type of operators, which are long strings sitting on top of the boundary, you don't probe the interior of AdS. What they try to argue is that you start really seeing the interior AdS geometry, let's say, you start really probing this, if you start going to correlate, you start looking at correlators where you take the limit where the vector flow charges are very large. So it's like you keep increasing the amount of times these worldsheets go around the boundary insertions, right? And because the picture is something like this, like this for a 4-point function, right? So this is kind of the picture you have in mind for low enough vector flow, where this goes omega times on this insertion point. But if you keep increasing the amount of times it happens, it's like you're putting more tension, right? And it starts going inside. So if I keep increasing omega, I go into something that goes more like this. Right? Because this omega, the amount of times they have to go, is very large. And I tried to argue that, well, I don't know all the details of the paper, but I tried to argue that if you look at correlators of such operators, you can start reconstructing the bulk geometry, even though it's a very stringy one. And then it's also true, you can also ask how much of, if I go to regimes which are not attention strings, so if I go to large K, how much remains of this kind of interpretation? I don't think it's settled because the boundary theory is not exactly a symmetric orbifold, etc., etc. But there is, in that case, too, for larger, and I'm going to write it in a second, there is an interpretation of a boundary Liouville type field, which you can identify with the radial field in AdS, but in clear AdS, even for large K. It's not the auxiliary, not necessarily the auxiliary field in the same sense like this, but you can identify. But I think there's more to understand there. I have the more precise answer, but I think it's more than just. It has a bit more meaning than it could in principle because everything is very. Okay, so I want to do a bit of the literature theory thing. It's not that short, so I won't be very brief about choreography beyond K equals 3. Everything I'm going to say is mainly based on the original kind of comments in this paper, and then these two very recent papers. But everything is still a bit under debate. What is the dual theory in particular for K larger than 3? So everything needs to be taken with a grain of salt. Everything is a bit more heuristic. Although there are some actual checks at the level of correlation functions and so on, but okay. Okay, so let me work in the unflowed sector of the theory. And let me consider one long string solution. Sorry, not in the unflowed sector of the theory, in the omega equals 1 vector, which would be the untwisted sector of the dual theory. So the long string with omega equals 1 has something that we already know, which is this, right? That's before it was set to the omega, now it's just z. And it also had, if you remember, I just wrote that phi goes like phi 0 minus omega minus 1 log mod z, right? So omega equals 1, phi is just a constant. This is the classical solution. So the idea of, and I will take this to be sitting close to the boundary. So the idea of this, of the paper by Steinberg and Witten long ago in '99 was to say, okay, let me try to give an alternative description of long string. So we already know one way of describing what a long string state is. One long string state is to take some state, for example, j m omega, where j has to be 1/2 plus is. And the rest, we take omega equals 1 in this case, and m is whatever it has to be, depending on m or h from we get from the Virasoro condition. So this is the picture in the SL2R Poisson-Witten model. Okay, fine. The idea of this paper is to say, okay, let's try to give another description of the same field. Let's try to say, okay, I'm going to be sitting on top of a long string solution. And instead of thinking about the long string as one perturbative state, one state inside the whole vacuum theory, I'm going to think about the long string solution as the vacuum solution, as not the vacuum, as my classical configuration, and try to describe small perturbations around that solution. Instead of small perturbations on top of the boundary, small perturbation on top of the long string solution, in this case, omega equals 1. Of this classical solution. And how do I do that? Well, I want to take phi to be some fluctuation. Starting from now, when I say phi, I mean phi the small perturbation in sense of this guy I'm going to be calling phi. And then I would do the same for gamma and beta, and for the rest of the fields of the internal sector of the theory, etc., etc. So let me focus on the AdS3 sector. But the whole point is that for gamma and beta, I can basically fix them. I can use the instead of trying to work in a covariant formalism, I can just fix them using, for example, the what we usually call the light congregation. So I take my field, which would be the classical field, which is Z, plus the variation, and I use the gauge freedom to fix this variation to 0. Again, this is the analogous of statement of being of doing strings in flat space and taking identifying x0 with tau and x1 with x1 with sigma. Okay, so when I do that, I have to look at what happens with the Virasoro condition. How do I write the Virasoro, the physical conditions, physical state conditions in this sector? So the Virasoro condition, you remember, was something like the energy momentum tensor in AdS plus the energy momentum tensor in the internal sector has to be 0. And then I had my whole my whole Wakimoto description of this thing, which was something like minus beta gamma, sorry, d gamma, minus 1/2 d phi minus my beautiful conventions u over square root of 2. And then I have the internal effect. This is the Virasoro condition. But now I know I'm sitting on top of a configuration where I fix gamma to be z, so d of gamma is just 1. Okay? And since I have always derivatives of phi, I don't care about the original constant here. Right? I just have the fluctuation. And the point is that I can use this equation to solve for beta. So this gives me that in the right conjugate, I just put beta on this side, and I'm gonna get minus 1/2 d phi minus u phi over 2 d squared phi plus where q phi, if you remember, was just minus 1 over k minus 2. And now I'm not setting k equals to 3. So this is my solution for beta in this. Okay, fine. So now I'm gonna come back to another piece of information that, if you remember from the second lecture, which is how we used in the Wakimoto formalism, how we use these fields to build the space-time symmetry, right? The space-time symmetry generator. So the Ln in space-time in particular for the Virasoro space-time symmetry. And you remember that the formula was something like this. So the Ln was something like the integral of this quantity here in my conventions, something like this. Then we proved that as long as the prefield description is accurate, then this acts on vertex operators exactly as the space-time, as the boundaries, Virasoro modes would act on the boundary states and so on. They generate the same transformation. Okay, fine. And now I want to look at what this looks like in this format. I know that in this setting, J plus is just beta, and J3 was something like gamma beta minus, I think, square root k minus 2 over 2 d phi. So I insert these expressions, and then I set gamma 2 with my other color. I set gamma equals 1 and beta equals this solution here. Sorry. Thank you. Okay, you do the algebra, and what you get is very simple. I first use I can write the final result. Let me do this. I just trivially get something like this. I first replace. Let me just write the final result. There's no big mystery. It gives me z to the n plus 1 and minus 1 over 2 d phi minus something that looks like this, where at some point, because here I had a z to the n and so on, at some point I integrated by parts to write everything as the power of, in terms of the power of z to the n minus 1. But this is what I get. Okay? And now you start looking at it, and you see that this really wants to look like a boundary stress tensor, right? Because the usual expansion is that I would write ln as the integral of the x to the n plus 1 as the boundary C, right? And so if z was the boundary coordinate as opposed to the worldsheet coordinate, then I would like to call this guy energy momentum tensor of the boundary theory. Okay, but we are not sitting at any random point, right? There is a kind of a heuristic way to think about what could be why data identification could be useful, because we are sitting in the sector where the gamma, I'm setting gamma to be z. We're sitting in the winding 1 sector, but we just identified in correlators, in particular for the classical solutions, we identified something like this would be related to the map gamma. And the map gamma in this case, because we are at omega equals 1, this gives me that it's going to be the trivial map. It's going to be something like this. Something like this, which is just x. So trying to identify that in this integral with what I would like to call x makes some sense. Of course, this is just a heuristic idea, but it's also true that there's kind of a bit more formal thing to say, which is that I know that the beta, the zero mode of beta is the zero mode of this current, which when I act on operators, I know that I identify with the derivative with respect to x. Okay? That I've been doing for several lectures now. But I know that the z on gamma gives me as the OPE minus 1 over z. Right? So B acting as the x derivative basically takes a derivative with respect to gamma, right? Up to this sign here. And so it makes sense to try to identify again z with the boundary coordinate x. And if that's the case, I would write here something like x to the n plus 1, and I would want to call this c of x. Again, this makes sense because I'm looking at the perturbations on top of a long string, which is sitting near the boundary, right? So if it's sitting exactly at the boundary, it's the perturbations of the boundary theory. That's the idea behind this way of writing things. But then I see that this is just some field. Like this. And what happened is that, first of all, we lost beta and gamma. Okay, but that makes sense because we went to light cone gauge. So we lost beta and gamma, which would be the fields to the space and the T and tau and sigma. Okay, fine. But the more important thing we did is that we ended up with a different background charge. Right? We ended up with Q. So this is a new background charge, which looks like Q pi minus 1 over Q pi, which if you use the formula I wrote here, and you just do the computation, you get this.
Where is the phi?
Sorry?
There is a d square phi, which is removed when you go from the previous line to the t of x.
Oh no, sorry, I just forgot to write. I'm just saying that this definition looks exactly like the phi plus internal sector of the worldsheet theory, but I shifted the background charge from q from -1 over square root of k minus 2 to k minus 3 over square root of k minus 2. And this starts making nice because this is trivial at k equals 3. So life is simple at k equals 3, but it's not trivial at k different from 3. It's giving me a clue about how holography works, wants to work beyond k equals 3. And you can check that it makes sense. Because if I take this correlator, this energy momentum tensor, and I look at the central charge associated to this T, right? Again, take into account that we're looking at the winding one sector. The winding one sector is what we identify with the untwisted sector of the graphic theory. So if it was a symmetric orbifold, which is not, but if it was a symmetric orbifold, it would be the central charge of the seed theory in the symmetric orbit, right? What I would get here. And I do the computation. In my conventions, when you have a, so if you had just a scalar field, you would have a 1 here for the central charge. If you have a background charge, this changes. In my conventions, you add some q squared, right? And then you add the internal guy, which looks like k minus 3 squared over k minus 2. And now the internal, I didn't say what the internal CFT was, but I can say what the central charge is because it's whatever it had to be to make the string theory consistent, right? So it's just 26 minus the AdS3 central charge. And lo and behold, you do the computation and you get 6k for any case. Which is exactly what Sumansu was hinting at last time when I said that I got this to be 18 at k equals 3. So this is the way you generalize that formula. And you can, I'm not going to do it here, but you can just play the same game with any. So if I do it at, if I start with the classical solution, so let's call this 1. If I start with the classical solution now, which for a long string with some omega larger than 1, you do the same computation, you do exactly the same things. There's a kind of there's a couple of subtleties in the computation because you have a 0-point energy contribution. You have something that you have to take care to take into account because there's some normal ordering effect when doing this, which is trivial in this case, but it's a bit more complicated in the other. But you finish the computation, you identify the same thing, and in the sector with winding omega, you get 6 times k times omega. Okay? Which again is exactly what you would expect if this was a symmetric orbifold, but we know that at the level of the dynamics is not. At the level of the long string spectrum, it is exactly the long string spectrum of the symmetric orbifold. But once you include short strings, it's not anymore. It doesn't work that simple.
Your omega plays the role of the strings because
No, so you can do this for any omega. You can now ask what's the largest possible omega that you can have in the classical configuration. And that's the number of strings in your background, because all you can do is take the whole number of strings that are there in your sourcing your geometry and put them all in a single, interpret them all in a single long string winding n1 times. That gives you the largest possible central charge, which would be 6k n1.
I don't think you can excite all the strings that makes the background. Like you can excite one because one is that will not back react on the AdS3. You can excite two that will also not back react on AdS3. If you excite all of them, then it's no longer AdS3.
It's again the same topic that we were discussing originally when Mariana was asking how you get this N1. It's always the same thing, right? At the genus 0, at really from the worldsheet point of view, you really only see like omega can go to infinity. You really only see N1.
That's because you sent
N1
number
going to
of strings to infinity because you are doing perturbation theory. Number of strings has been sent to infinity.
Exactly. So it's a bit hard to see that N1, but the heuristic is the same as I was arguing. When doing the space-time symmetry. The second leg.
Yeah, C tau is basically the eigenvalue of this I operator that he wrote.
Exactly. Yes.
Numbers of two.
Okay. So you can look at the spectrum in the long string sector. And the difference with what I did last time is that I don't take k to be 1/2. I take the general possibility, and I don't take k to be 3. I take k to be anything, right? Anything larger than 2, because at 2 I have unitarity problem. You look at the spectrum. I'm not going to do it again. It's just a trivial consequence of the Virasoro condition, and you get C, let's say 1 over 24 omega, this guy here, minus 1 over omega, plus exactly what I had before, which is the internal part divided by omega, plus, and now I have an extra contribution, which I can write in this way. I can write as, let's call it beta u minus beta over omega, where I not to yes, where I define beta as k over 2 minus k minus 1 over square root of k minus 2. Again, this is only for the long string sector. That's important. And so you see that this is exactly what you would expect for the spectrum of a symmetric orbifold of, say, N1 copies of a theory, which now is not just the simple thing that we had before, but it looks like some non-compact scalar field with some background charge Q, which I define here, times the CFT of the internal sector. And where are these guys, where is this contribution to the weight coming from? The contribution to the weight is because in the seed theory, the operators are just defined as some internal operator times, again in my beautiful conventions, some exponential, some vertex operators, exponential in this non-compact scale. And if you compute with this energy momentum tensor, this sector here, if you compute the weight of this guy, you get exactly this thing. And then if you add to it, so you have some label beta, some label H int, and then you add some label omega, which is that I put here some twist operator, right? And then you get exactly this vector. So far so good? Yeah? Yes? No? Okay. Fine. So there are two important things to say here. Fine. So this doesn't work for short strings. and now does it match the worldsheet correlator that we computed for general case? And again, a trivial way to see that it doesn't match the worldsheet correlators is that if this was a holographic theory, then all correlators would be 0 unless some covering map exists, and we know that there are contributions, there are correlators on the worldsheet which are non-zero even when the covering map doesn't exist. So it's not, the holographic theory is not this. And the proposal from the, well, I maybe erase it here, from the recent proposal from the papers in 2021, where the Martinek et al. Paper was for k smaller than 3, so between 2 and 3, and the Eberhard paper was claiming a similar thing for k larger than 3. And there's a very important difference between these two. I'm going to say a couple of words now, but there's a very important difference because the sign of the background charge changes when you go from k larger than 3 to k smaller than 3. It goes from positive to negative. So the proposal is that it has to have some twist 2 deformation, the marginal deformation, given by some operator, which should be twist 2. It should be twist 2 because it should break the symmetrical default structure, so it should entangle it should allow me through the deformation to get non-zero results for situations where in the symmetrical default I had 0 results, and it has to be some kind of potential, some exponential, or some potential for phi, right? And why does it have to do that? Well, it has to do that because if this was a theory by itself, then this field phi would be exactly holomorphic, or the derivative would be exactly holomorphic. But we know that if there is a relation between this guy in spacetime and this guy on the worldsheet, we know that this guy in the Wakimoto variables is not really holomorphic. Right? We know because there is an interaction term when you go inside the interior of AdS. Right? There's an interaction term which breaks, in particular, many things, but it breaks the Wakimoto field, the fact that the Wakimoto fields are holomorphic. So there should be some non-trivial potential here. That should be part of the deformation. And just very briefly to give you an idea, you can ask, what deformation? And there are several ways to try to argue how this should be. But again, for me, the nicest comment that one can make is, we know what's the deformation in the bulk. We know it. It's a Wakimoto interaction term. Right? The bulk. We know that this looks like interaction Lagrangian, look like beta bar e to the square root of 2 u I pi. And so the first intuition that you could have from this is that we know more or less what changes we have to do to reinterpret things in terms of the boundary theory, right? We basically have to speak in terms of this boundary coordinate x, and this beta are basically derivative with respect to x. And we know we have to interpret, we have to change the background charge from Q5 to this new Q, right? So at least intuitively, one possible proposal would be that this by 2 is something like dx bar e to the square root 2 q pi for the new q. This would be the bulk version and this would be the boundary description. And you can check what this does, and you can say that you can see that this. You can say it in a much more explicit way. I really don't have time to get into that. But you can see that this proposal actually makes sense. It actually changes the equation of motion of your boundary theory in exactly the kind of analogous way as this guy changes the equation of motion in the boundary. And the main discussion is that you have to go from this q phi to this q. And then there are many details on checks on how it works and the fact that what are the corrections to the worldsheet correlators and what are the corrections from this guy to the boundary correlators and how you can use it to actually check things. And you can be a bit more precise because here I'm doing Wakimoto variables. You can do it a bit more precise. And you can show that if you want to take this formula and get a marginal operator, you have to set some particular values of, if you want to have h being 1, and this can be achieved by taking omega equals 2, h internal being 0, and what do we want, and j, which I wrote, okay, fine. If you plug these guys into that formula, you find that this whole thing adds up to 1. Right, and you do the same on the anti-holomorphic sector, you get a 1,1 operator in spacetime, which should be your marginal deformation. And you can check that this value for j corresponds to a potential, to an exponential type wall for phi, which is exactly like this one. Again, I'm being very sketchy here, I'm not saying much more because I don't have too much time, and also because it's not completely well understood, at least for K, large K. But I just want to give the idea that there is some kind of precise proposal for what this boundary theory is. Although, again, so the idea is the definition is perturbative. It's not a non-perturbative definition. It really depends on saying, okay, I start from some symmetrical ripple points and I add some marginal operator to the reaction, and this will define my boundary theory order by order. Then I can try to match correlators order by order, and that's part of what was done by Eberhard and Andrea Day, and originally, in some cases, for k smaller than 3 by Martinez, Kutasov, and collaborators. However, there's an important comment here, which is there's a very big difference between k smaller than 3 and k larger than 3. And again, where the proposal works in general is very is still under debate. So if I look at k smaller than 3, between 2 and 3, and k larger than 3, there are very different things that happen. Because if you remember, I had for the short strings, I had a bound which was like this, right? So in this sector, the bound on the short string sector is 1/2 minus j smaller than 1. So in particular, j equal 1 is excluded. And this means that the SL2R vacuum is not in the spectrum, which is something very similar that happens to what happens in Liouville theory. Similarly, this implies that the BTC black holes are not in the spectrum. they become non-normalizable. And importantly, the long string states become free at phi going to infinity toward the boundary. So the whole discussion that I did makes sense because you can really interpret these scattering states as states going from infinity where they are free. You define the operators there and then they scatter inside of AdS and go back. Yeah.
What does it mean that the vacuum is not in the spectrum?
It's exactly analogous to what happens in Ljubich theory. In Ljubich theory, you define your. So one thing is if the operator is there through the state operator correspondence, which it is there, it's always there. But then another question if the associated state is normalizable. And in Ljubich theory,
it's not normalizable.
Yes,
Okay.
it's not normalized.
Okay.
It's not in what you would call the spectrum of normalizable state.
Okay.
Yeah.
And the fact that BTCs are not normalizable, you are saying that it follows from the fact that the vacuum is not normalized?
Yes, because the BTCs are just an orbifold of CFT2 vacuum.
Okay, but then, but in the original spectrum, like for k larger than 3,
There are BTCs. Yeah.
how do you see those BTCs from the worldsheet?
You will never.
No, you can define the worldsheet theory on orbifolds and so on. I mean, there are different ways of trying to argue for that, but not from the worldsheet itself. They are heavy states.
Yeah, the fact is, I don't see how you can conclude that BTC are not normalizable if they're not even in the spectrum and you don't know how to, like, you have to quantize your theory on a different background.
You're trying to think about you can think about the Cardi argument, right? You think about the space-time theory, you have your vacuum, and that the fact that you have your vacuum defines the high energy behavior of your theory due to modular invariance. If you remove the vacuum from your state, your set of normalizable states, you're also changing how the high energy sector behaves. And
yeah, I understand hand waving why this is, but it doesn't seem like completely clear to me.
No, directly from the worldsheet picture is not that easy to see. I agree.
From the worldsheet picture, I would say that you take the Euclidean continuation of that, and then you take whether the time circle is contractible or phase circle is contractible.
Yeah.
Both are nice worldsheet theories, but the energy of one is the vacuum, the energy of the other is like very high.
That's exactly what we were talking about like the other day at lunch, right? Like whether this duality in target space between AdS3 and BTC, whether it's respected at the level of the string theory, right? Like whether I quantize my strings on two different backgrounds.
Not at the level of the partition, at the level of the spectrum.
Yeah.
But at the level of classical supergravity solution.
Yeah, agree.
So that's I think what he's got.
Okay, I see.
Well, here supergravity is a bit strong word because there is stringy, but
okay.
Okay, and then for k larger than 3, the opposite thing happens. You have the vacuum in your spectrum, normalizable spectrum, you have your BTC states, but what's more annoying is that these long string states, because you change the sign of this Q, so you change the sign of the potential. So instead of having a nice potential in the infrared and the theory being Fred in the UV, you change it from the side of the exponential wall. And so now it's harder to argue that the long string states are well defined near the boundary. And in this case, the idea, this proposal by Eberhard, is that you kind of work in this setting to get analytic expressions in K and then do some kind of analytic continuations to K larger than 3, which seems a bit odd, but then at least at the level of some of the correlation functions that were looked at, it seems to make sense.
Do they have checked that this analytic continuation works?
As far as some residues of some of the correlation functions, yes.
But if the spectrum is different,
yeah,
like in the two cases, then for sure the partition function should not
Yeah, I agree.
between the two, even after analytic continuation.
Yeah, it's happened. It's not really certain.
Analytic continuation is not at the level of partition function.
No, I mean just I compute the partition function for k between 2 and 3. And then I just set k.
I don't think they will agree.
Yeah, I don't think so too. Yeah.
They will not.
Yeah, exactly.
At least for some of the correlation functions, it seems to work.
And sorry, one more question.
All the questions.
Because all this like k less than 3, I don't know it. It's very weird. So for k larger than 3, I should think that the partition function is Mandelson algorithm.
Yes.
Right. But for k between 2 and 3, it's some different expression which has been computed, or
You know the spectrum, so I mean it's
that's
trivial to compute.
I don't know if it's written anywhere, but
okay. And then for k below 2, there's
maybe it's not. It's just non-unitary. That doesn't make because
k equals 1, right?
no, that in the Botanic language that's k equals 3.
Sorry. Okay.
Doing everything in Botanic here. There's always a shift in 2 units when you go to supersymmetric. Okay, now in the last, that's all I want to say about choreography beyond k equals 3. And in the last, let's say 15-20 minutes, I want to talk a bit about a different application, which is little string theory. I mean, the whole discussion is interesting because from the worldsheet point of view, everything is kind of easier to compute. And the natural setting to look at is large K, right? Which is where you have the description and so on. So you just have a worldsheet description for that, which is more precise. But then from this point of view of what the holographic theory is, actually K larger than 3 is much more cumbersome. It's not that nice. And so I think it's still a non-trivial. It's still an open question whether that actually captures everything you want. Okay. So let me mention a bit. Let me switch gears and mention a bit what is called little string theory and why I want to talk about. So little string theory is the following. Let's say I have a set of only NS5 range in flat space. And there are N5 of them. I'm looking at relatively small n, so looking at big couplets. I can write down what the solution is for this guy. I can also add some strings if you want, but I can consider what the fluctuations of this configuration is, right? So in principle, I have the definition of the dynamics of the things are the dynamics of the on the NS5 plus the dynamics on the bulk, so the closed strings plus the interactions between them. The usual setting, right? It's a bit different because now I'm not talking about D5 frames, I'm talking about NS5s, but okay. So I have some dynamics by some action like this. Another question is what happens? So it's defined by the usual two quantities, alpha prime and G string. And now I can ask what happens in the limit where G string goes to 0 and alpha prime is fixed. So normally you would kind of, this was the brain, you would kind of think that G string goes to 0, kills all the dynamics. So the theory should be trivial. But actually, while it's true that in the limit G string going to 0, this goes to 0, and this goes to 0, I mean this decouples, and the interaction goes to 0, it's not true that this theory here is trivial. One way to see it is if you go to the S2L picture, you're going to have in type 2b, you can do the similar story in type 2a or the NS5 in type 2a, but in type 2a, you go to the S2L picture, you have a set of D5 frames. This has a low energy gauge theory description. And you can ask what the coupling is, the Young-Mills coupling on the D5 for this theory, and that's exactly the tension on the D5, and that's written like 1 over alpha prime G3. Okay? Okay, nice. And now, under S duality, I get G string going to 1 over G string, and alpha prime going to alpha prime times G string. Right? So if these are the quantities in the D5 setting, the limit I was taking corresponds to G string going to infinity and alpha prime going to 0 with alpha prime times G string fixed. Right? Because I just have, this is the old, this is, if I define this as being my new guy, then this is 1 over the old one, which was going to 0. And again, this one is the new guy, but then this was fixed, and then this is going to be fixed. I'm just doing S duality on my limit there. So this is fixed in the limit. So this is telling me that in the NS frame, the coupling, the effective coupling on the NS5, which again in type 2b has some kind of HC description, is actually 1 over alpha prime, which is fixed in my limit. So while I took G string to 0, the theory on the NS5 is actually an interacting theory. Then what happens is that I started from a critical string theory, from a 10D string theory. I wrote down, I included some NS5 brains. I look at the dynamics of that, and I take the limit G string going to 0. This trivializes all the dynamics of the bulk strings, but it doesn't trivialize the dynamics on the NS5. Okay? But I haven't sent alpha prime to 0, which means that I'm not really doing a low energy limit. Right? So alpha prime is fixed. Then the theory on the NS5 is still a string theory. How do you know it? You know it because if you start from the 60, from the low at low energies, I have a 60 Young-Mills description. But 60 Young-Mills is not a normalizer, right? I have an energy scale in my cup. And you can ask, what are the new degrees of freedom at energies of order of 1 over the square root of alpha prime. And actually, if I have a bunch of NS5, this is going to be N5 square root of alpha prime. I can ask what are the degrees of freedom that are here, and the answer is that the 60 in 60, when you have a Young-Mills theory, you not only have the basic gauge field, but you also have instanton contribution. But because you are in 60, instantons are string-like objects. They have their one dimension, right? So these are the instanton strings of the low energy 60 Young-Mills theory. How do you know that? Well, you know it because, again, these are going to scale like 1 over the effective Young-Mills coupling, which is 1 over n5 square root of alpha prime, 1 over n5 alpha prime. Should have had. Yeah, this. Okay. But this is almost like a string tension, right? Except for this n5 here, right? The tension is lowered by a number of, by how many strings I have. I might be missing a square root here. No, I think it's fine. And because of the fact that these 60 instanton strings have a tension that's lower by a factor of n5, these are called, in this frame, these are called little strings. It's in the wrong order here. Okay, I might be doing some mistakes. Think of for long strings.
Yeah, it's smaller. Yeah, length is longer, but tension.
The other way. Yeah. So the factor should be upstairs.
I think the tension is small, the length is long. That's right. So you thought was between.
Okay. Thanks.
Little in the sense that tension is small.
Yeah.
Why are you calling it a Young-Mills theory? It's not a Young-Mills theory, right? It's NS5 theory on the NS5 braids, which is not.
Add low energy in fact to be. It has a gauge theory.
No, because there is no DBI type action, right? Well, in D5 maybe yes. Okay.
These are the, if you want, these are the instanton strings of the dual thing. This is it. Okay. So this is a 60 non-critical. And retains some of the features of being a string theory. For example, it has the duality, right? There's little things, there's type 2b little things and type 2a little things. It has this energy scale and so on. And also it is non-gravitational. If you look at the spectrum of this guy, there are no spin to mass fields. But still, it remains a non-trivial string theory. And so this, since this is a theory, on the NS5, you can ask, as we do for theories on the brains, you can ask if this guy at large n coupling, does it have a holographic description? Again, the theory on the brains on this n side is not a free theory, it's a string theory. In particular, it's not a CFT. So if there is some version of holography, it's a non-AdS holography. And the answer to that is yes. There is several ways of seeing that this has a holographic description, and it's given in terms of what I usually call asymptotically linear dilaton theorem. Or string theory on asymptotic linear dilaton back.
How many dimensions?
The back in terms
Okay, so
the dual description is the bulk supergravity solution in the D.
so it's not one the boundary theory is D and the bulk is D plus one. That's not false.
Yes, we
Yeah, in the set we have D plus one non-compact directions and up D.
it's n-dimensional.
Then it is like the usual AdS3. You have the bulk is actually 10 dimensional, not really D plus
Okay, yeah, but the CFT is the 6-dimensional.
Yes.
Yeah,
Not a CFT.
Not the
not
CFT.
the CFT. Yeah, okay. The boundary theory
Is
is 6-dimensional. In the back, you have 7 non-compact dimensions and 3 compact ones.
The bulk is basically this linear dilaton times.
I'm going to write the solution. Okay, so in the last minutes, I will try to say that there are 3 different ways of understanding. I won't have time to go into any detail. I guess there are 3 ways of understanding the same theory, same dual. One of them is in supergravity. One of them is on the worldsheet. And one of them is from what are called single trace CT bar deformation of the original CFT. And anyway, the expert in the room is Mark here. What's happening? Okay. So supergravity, I can take for simplicity because it's gonna end up being better defined. I can add some F1 things into the game. I write the background associated to NS5 plus F1 system in flat space, and I get something like this. Okay, and then I get 4 extra directions. Okay, where I'm defining F1 and F5 as the usual harmonic functions. So F1 is alpha prime G string square and 1. over the before volume of this guy if it's compactified r squared, and f5 is 1 plus alpha prime n5 over r squared. Okay. Normally, what we do this is the original solution we started from in the first lecture or in the first pages of the notes. In what you normally do in order to get to AdS is you kill the one in the harmonic function, right? You rescale the radial direction with r going like alpha prime and alpha prime to 0, and then you kill the 1 plus here and the 1 plus here. If you do that, you get something that looks like AdS3 cross S3 cross T4. But if you take this limit that I defined here, which is drifting to 0 and alpha prime fixed, you see that when you rescale r being this string times some r which is fixed, let's take r over this string also fixed, you see that the effect of this limit is that you kill this one here, but this one remains. Right? I just rescale r, and then I write in terms of r tilde, and I kill this guy here. Alpha prime is fixed, so this one remains. And so at the end of the day, the solution takes this form. Okay. I define some new coordinate phi. Yeah, I, phi. And also you can check that at large phi, this phi goes like the log of r with a minus sign, and at large phi, the actual standing dilaton behaves like this phi coordinate. Right, so this phi is the kind of the new radial coordinate in this identification of this sort. I would say that you check that at large radial distances, you get a dilaton which goes linearly with this radial guy. Okay, and so this is a theory which interpolates between an asymptotically linear dilaton background and in the UV and an AdS3 background in the infrared. So it's like extending the original AdS3 solution back into the UV up to some limit with that to asymptotic linear dilaton.
So UV IIR, you mean in the radial AdS direction, and the asymptotic linear dilaton background is flat space but with a linear dilaton.
Yeah. Yes. In string frame. In defined frame is negative curvature.
Right. So this is the supergravity solution that's holographically dual to this model here. And then I'm getting out of time, so let me just say the slogan here. You can actually extend the worldsheet model that we had to this full space. You can actually extend the worldsheet model, which was only for AdS3, because you can check that this model now, this geometry, is still a coset space. So you can still have an exact worldsheet description which you can see as a marginal deformation of the original SL2R CFT was a node. So you add some J bar deformation to this thing. This again has an exact description, and you can build the worldsheet theory in this full background until in this decoupled background, but decoupled in this sense here. And you can extend the formalism that we are using to compute correlation functions, to compute partition functions, to compute a lot of things about this holographic theory, which was about this NS5 theory, which interesting theory, which remained kind of mysterious in many ways. A lot of people worked in this. Sumangsu, Kutasov, Gibeon, our collaborators, for example, Luis Apollo and Wei-Song, Monica and Sylvia as well. A lot of people we know. And you can actually build the dual of this, build the worldsheet theory exactly and use it to compute correlators exactly, even though you still have a CFT on the worldsheet, even though the boundary theory is not a field theory anymore. And the third description for this is to say, okay, I started from, so here I have in the geometry, I have an AdS3 cross S3 cross T4 space, and I add to it, I extend it into the asymptotically linear dilaton region. Here on the dual side, I have some CFT2, and as it turns out, you can define something called some type of TP bar deformation, which is an irrelevant deformation. And it has it has to be a specific source, which is usually called single trace, for which reason which are framed in the notes, but I don't really have too much time to say much about it. But the point is, you can actually, from the CFT, from a dual CFT point of view, you can define some highly tractable irrelevant deformation, which deform the theory into whatever this interesting theory is. And so this gives you in principle, it will give you a direct way to describe the interesting theory. And this is where I kind of want to stop. For me, the story is interesting because, again, up to recently, it was not that, even though this theory was defined a long time ago, it was not that clear how you could compute correlators and study many things about it, because it's a complicated non-gravitational string theory. And the new developments have been mostly on this side, have been mostly on saying, okay, have actually two concrete ways of going and computing correlators in this theory. One is purely from the worldsheet in terms of this cosset model, and the other one is from the deformation of a CFT, which is a particular type of irrelevant deformation which many people have been working on over the last year. And again, in both languages, you do have a concrete handle on how to compute things in this decoupled theory. But I don't have much time to say more, so let me stop here.
What does it mean that if you do this single trace TP bar deformation to a 2D CFT, we go to a little string theory? Like, how many dimensions is a little string theory defined? Like, what is it?
You can still think, so the idea is that here what you have is you have this little string theory, but compactified on a T4 side. So the effective theory is two-dimensional. So it is a non-local theory, but defined in 2 dimensions. If you can.
What you do with this TT bar deformation is you start growing the extra dimensions that you had compactified, or?
No. You just you add new kind of UV degrees of freedom in your theory. The four extra dimensions are still compactified.
So the theory is still two-dimensional.
Yes. Yes. So this is useful if what you want to do is study this 60-string theory compactified on T4.
Okay. Which now will be some two-dimensional QFT, which is not
It's not a QFT.
invariant.
It's not a local theory.
It's not a local theory at all.
Sometimes it's called two-dimensional little string theory.
Yeah. Okay.
No, thanks, Nico.